All right, guys. So I promised you a review session for right-hand rules, and so here it is. I've got several of them up here on the board, and a little bit of problem solving at the end, and so hopefully we'll be able to get through a couple of those and get you a little bit more comfortable with it. Having it up on the board hopefully will help you imagine this being your paper. A couple of things just before we get started that have helped a couple of people is recognizing that when we do this, you're always looking at the perspective of your paper, right? If your paper is up and down like this may be your computer screen, up and down, that means this is up, that's down, right, left, into the page is towards the board, and out of the page is away from the board towards me, right? If you're looking at it flat in front of you, then perhaps this is up, that's down, right, left, into the paper would be down into the page, and out of the paper would be up, again, towards me as I'm looking at it, right? So your perspective has to change. The other thing that's helped a couple of people, if you can't get your hand, the parts of your hand have to be right angles, okay? So if you can't get your hand to do that properly, turn your paper, right? Just make sure your finger's pointing in the right direction, and everything should turn out okay, even if you have to shift the paper in order to do it. All right. So with that, let's go ahead and go into it. Let me remind you of the 3 right-hand rules. The first right-hand rule is finding the magnetic field created by a moving charge going in a straight line. So if I got a moving charge going in a straight line, my thumb represents the charge moving in that straight line, and my fingers represent the magnetic field around that charge. Now, this could be a charge all by itself, or it could be charges inside of a wire moving along, right? Now, one thing to remember is that you want to keep your fingers at a right angle. If you want to try to find the magnetic field at a specific point, the thumb needs to be wherever the wire is. You bend your fingers at a right angle. So above, it would be coming towards you. So that would be out of the page or into you, right? This direction, whatever you want to call that direction. If I go like this, then something on this side of the wire would have a downward force. And so depending on where you are, thumb should be on the wire or on the particle. And then the bent fingers bent at a 90-degree angle right here. That 90-degree angle should then represent the direction of the magnetic field at the point where your knuckles up here are. Okay? Second right-hand rule. The second right-hand rule is when we have a charge going in a circle or in a loop, or it doesn't even have to be a circle. It could be a square going around a square like this, or a rectangle. As long as it's going kind of around and around, then what we can do there is we can say, well, the current is doing this, or the charge is doing this. Your fingers are representing the motion of the charge, and then your thumb is representing the magnetic field inside of your loop. Okay, on the outside of the loop, it's doing exactly the opposite thing. So if I'm going like this, then my magnetic field is this way inside, and then it's coming this way on the outside. It doesn't matter whether you're above, below, sides, but it's going the opposite direction. All right. The last right-hand rule is this one right here. Okay. And with that one, the finger represents the motion of the particle. The bent fingers, again, bent at 90 degrees, need to represent the direction of the magnetic field. And the thumb then, again, right angle. You'll notice that it's a right angle here as well between the field, and all of these have to be right angles. You can't do it like this, okay? That's not a right-hand rule. That's sign language for, I don't know, something. So don't do that. Right hand, nice and perpendicular, okay? The thumb is then pushing the particle. That's the force that it will receive. Now remember, you got right-hand rule for positive particles. You've got left-hand rule for negative particles. You could always, for negative particles, you can just do the right-hand rule, and whatever you get, the negative would have to be the opposite, okay? And so hopefully we'll see that as we go through some examples here. So without further ado, here we go. Let's go through a couple of examples of the right-hand rules, okay? So here we go. We have current flowing to the right, and the question is, which direction is the field created by the moving charge? Okay, so the field created by the moving charge, that means we're going to use our first right-hand rule. The current is going this way. And so you'll see my curved right hand up on the top. you can see that when I put my thumb on the wire there, and you can put your thumb on your paper here or on your computer screen just like that. And you may have to turn your body or something, but the thumb should be pointing in the direction of the current. You see that the fingers are pointing outside of the page, which means that up above the wire, the magnetic field is coming out of the page. And so we put dots. Remember, the dots represent the tip of the arrow, which is coming towards you. I can put more dots up here, right, to represent coming out of the page. Okay? Now, what if I want to know somewhere else? Well, if I wanted to know below, then I've got to rotate my hand, right? I got to rotate my hand like that. And maybe I need to rotate my paper or something that allows me to do that. But the thumb needs to be going this direction. And then my fingers, if I want to know what's happening down below the wire, then my fingers need to be below my thumb, below the wire. And so I go like this, and you can see hopefully that means that the magnetic field is going into the paper there, into the board, just like that. And there you go. You got the magnetic field around that one right there. Okay, let's try the next one. So this one we now have, it says that the current, remember, is always referring to positive charge. Even though we know that it's the electrons that are moving, current is the positive charge. All right, so current here, it says the current, it gives me an X. So it's saying the current is going into the page. So again, we want the field. And so because it's going a straight line into the page, again, I'm going to use my thumb because the thumb is representing a straight line. So I'm going to go straight line into the page. And again, I'm going to hold my fingers at a right angle. You'll notice straight up and then right angle. So up above, you can see that the field is going over to the right. Okay. If I turn my hand, I can see over here where my knuckles are now, I can see my fingers are pointing down. If I go still thumb into the page, I rotate down this way. You can see now that the fingers are pointing over to the left, right? And then we can try to go, oh, my arm doesn't go that way, so maybe we go back this way. I come over on the other side. There, you can see right there, my fingers are pointing upwards over there. And so what we see is that the magnetic field is going around. Obviously, I could have chosen any other points. I could do there, I could do there. You can see what it looks like at any point going around that wire. So the magnetic field goes like this around that wire. Okay? Next one. Next one's right here. So this one we're connected to a battery. So the battery goes up here, it goes around the loop, just like this. So you can see the current going in a loop here. Now, because the current's not going in a straight line, it's going in a loop, then we're going to need the second right-hand rule. Now, the second right-hand rule, remember, our fingers are going to represent the current, and then our thumb is going to show us the magnetic field inside the circle. So fingers are going around like this. And if the fingers are going around like that, the thumb must be pointing into the page. So inside, I've got a magnetic field going into the page. Now, if it's going into the page there, it must be coming out of the page everywhere else around it. All right, so there's our magnetic field going into the page there, coming out of the page on the outside, into the page, out. It has to be a circle, has to be a complete circuit, right? And that's what we see right here. Now, for those that are curious, yes, you could actually use the other right-hand rule. You could say, well, what if I just say that the current is going this way at the bottom? Well, look, my fingers, current, magnetic field, into the page. Look at that. What if I look at the current up at the top? Because some of you saying, yeah, but on the top, the current's going the other way. And I say, okay, well, let's go the other way then. If I've got my current going this way, oh, dang, look at that, my fingers into the page, right? It doesn't matter. As long as I'm going clockwise like this, if my thumb is pointing in that direction, my fingers are always into the page, all right? So there we go. Last one. We've got a negative particle here. The negative particle is moving down. So what will its magnetic field look like? So because it's a negative, I'm going to use my left hand. Secondly, because it's moving in a straight line, I'm going to use the first right-hand rule. So I'm going to say, okay, it's going in a straight line, which means over here, it's going into the page, right? You see my fingers right there, curved, nice and right angle. going into the page there. And what happens is I go around in the back side, it's going to be going this way. Over here, look, my fingers are pointing towards you now. So then dots over here. And then if I wanted to, I could do something like this. And you can see that in front, the magnetic field would be pointing over to the right. Now I can't really demonstrate it on my board, but get that idea that it's going around the particle like that. Now, again, I could have used the right-hand rule. I could have just said, oh, well, if it was going down, it would be into the page over here, but it's negative, so it's got to be the opposite out of the page. And then when I came over here, again, down should be out of the page, but because it's the opposite, it's into the page. So there you go. That's your first couple of right-hand rules. Let's step on to another set of questions here, in which we'll look at a charge moving in an external magnetic field. So because the charge is now moving in another magnetic field, right? All of these, we were looking at what was the field being created by the charge. Now we know that a moving charge is going to create a field, right? For example, this positive charge right here, it is going to create its own field. We're not really worried about that right now. We know that a positive charge is going to create a field going into the board there and out of the board over here. So this is not the field created by the positive. It's an external field. It's another field that's being added in. Now, because this positive charge is creating a field around it, those two magnetic fields will interact with each other. And that's why we get a force. And so what our concern here is, what is the force? All right. And so here we're going to use our other right-hand rule. We got our velocity, we got our magnetic field, and then we got our force. So here we go, positive charge moving upwards. You see the magnetic field, which is coming out of the page. So because the magnetic field is out of the page, I can't do this because my fingers are pointing into the page. I got to turn my hand around like this. So now you see my fingers still pointing upwards in the velocity of that positive. My other three fingers are pointing out of the page with my magnetic field, which means that my thumb, or the force, is over to the right. Got it? Next one. We've now got an electron that's moving over to the right, going through a magnetic field, which is directly down. All right. So again, you could use either rule. I'm going to start off with my left-hand rule because I can. And so here goes my electron into the field. My finger's pointing the way that it's supposed to go. My other three fingers need to point the direction of the field. Oh, well, that's convenient. And what do we notice? The thumb is pointing straight towards you, straight towards you. And so if the thumb is pointing straight towards us, then we just say the force is out of the page. Just like that. Force is coming out of the page. Or you could draw a dot on there and say that's the force, right? But to make it clear, I'm just saying the force is out of the page. Now, I could have done it with my right hand, right? I could have said, up, go in that direction. I need my fingers to point in the direction of the magnetic field. So I'm going to turn until they're pointing in the direction of the magnetic field. Notice that my finger's still pointing in the direction of the velocity. My other three are now pointing downwards. And which direction is my thumb? My thumb is into the page. Keep those right angles. Into the page. But because it's negative, it's going to be the opposite. Out of the page. There you go. Let's try a different one. Let's try a slightly different one. This one right here, we got current going through a wire, which is in a magnetic field that's going into the page. Remember, current is, we're talking about the positive, even though we know it's the negatives that are moving, but we're talking about the positive. So we say, all right, right-hand rule. Current's going this way. Remember, this would create a field, right? The field created by this would be into the page there and out of the page there, right? So we have to remember that it is creating a field, but that's not what we're interested in right now. We're worried about what does this wire do when it's in this magnetic field provided by some other source. Well, charges, positive goes that way. Magnetic field is into the paper, which means the force is upwards. And so the force on this wire is upwards. And it would be everywhere, right? Anywhere where there's a positive charge moving, it's going to have a positive force upwards. All right. Hopefully you're doing all right. We're going to move on to the last one before we get into some problem solving. This is kind of an interesting question right here. I've got kind of a loop in the field. All right. I got the field going to the left, but I've got the current starting down here. It's flowing up around here and going back down to the bottom. Now we're going to look at three different pieces of this to see if we can figure out what's going on and what the force will be to that loop. All right. So we're first going to look at the right-hand side. Okay. So on the right-hand side, we've got the current going up. We've got the field pushing to the left. So I got to make sure that my finger is pointing up and my 3 fingers are pointing to the left. So you see, I already know I got to turn my hand around that way. So velocity up, field left, and I see that the force is out of the page. So I'm going to write over here that the force is out of the page. All right. Now I'm going to look at the current up here at the top, because if the current's changing direction, it might change the force. In fact, it should. So here we've got the current going this way, right? Current's going this way. The field is also that way. Now, what that does is that means that my 3 fingers need to point in the same direction as my pointer finger. That's the problem. If they're parallel, remember the force only happens if they're perpendicular. If they're not perpendicular and there's no perpendicular component, there won't be a force. All right. Notice that if I point these 3 fingers in the same direction as my pointer finger, then my thumb could literally be pointing in any direction. That's a problem. And so here we say no force. So this side is being pushed out of the page. Up here, there's no force. How about over here? Let's see what's happening as the current goes down the loop. All right, so again, I need my right hand rule. I need my finger to be pointing downwards, and I need my 3 fingers to be pointing in the direction of the field, which is over to the left. Okay, so velocity, I'm going to have to turn this way, I guess. Okay, so velocity, field, right? These 3 need to match up with the field. And look at that, my force is into the page. So what would happen? What would happen if we're pushing outside of the page on this side and into the page on that side? What would happen to my loop? It'd rotate, right? This side would be coming out of the page. That side would be going into the page. And so we'd be getting a rotation of that electrical wire. Pretty cool, huh? We're going to see that a little bit more later. Okay, it'll come back to us soon. But for now, that's enough. We were able to use our right hand rules. We were able to figure out exactly what was going on there. Pretty cool, huh? All right. Come with me. We're going to do a little bit of problem solving. Okay, I don't know if we would have gotten to this if we did this at lunch, but because it's just me right now, we're going to go ahead and do it. We can actually get through this. All right. So here we go. I got 4 problem solving questions for those of you that are really looking to dig a little bit deeper. All right. So first, we've got a wire with current going that way, and we've got an electron that's moving up. And the question is, what directional force will the negative charge feel? Okay, so what force will this guy get? Okay, well, why would he be feeling a force? Well, he's feeling a force because there's a magnetic field being created by this wire. Right? So the first thing we need to do is we need to figure out what is the magnetic field created by this wire. All right, so that would be my first right-hand rule. I'm going to have my current going this way. My field, look down below the wire. When I'm below my thumb, my field is into the page. When I'm above my wire, the field is outside of the page. So into the page here, so it's going to be like this. And then above the page, above the wire, it was coming out of the page, just like that, right? So into the page, out of the page. So look at this. This electron now, or this negative charge, we see that it's going through this field into the page. So now we can find the force, right? We can say, well, that negative electron, I'm going to go left-hand rule because I can. We go up. The field needs to be into the page, which results in a force to the right. How about them apples? Yeah, we do it with the right-hand rule too, right? We should say up, fingers, into the page, right? Up, into the page, and you'll notice that my force is over to the left, but that's because I use my right hand. Because I use my right hand, it's going to the left. Therefore, because it's a negative charge, it's going the opposite direction. That's over to the right. All right. All right. All right. That wasn't too bad, right? We just had to put the two ideas together. That's what problem solving is taking simple ideas and putting them together to figure out a more challenging problem. All right, here we go. Number two. Number two, what direction is the field here? So what we see is we see a negative particle that's moving to the left, and yet it has a force downwards. All right, so it wants to know what direction is the, I guess I should have clarified, what direction is the magnetic field? I guess the electric field would be completely different here. So what direction is the magnetic field? So we've got the velocity that way. So it's a negative charge. I'm going to use my left hand. Okay, so the velocity is going that way. So I'm going to come over to this side. Velocity that way. Now it says the force is down. Now remember, the force was my thumb. And so I need my finger to be pointing that way and my thumb to be pointing that way. But I still got to hold this, all those lovely right angles, right? So going to the left, I'm going to have to turn my hand, keeping that shape so that the force is downwards. And what direction are my fingers pointing? They're pointing out of the page. They're pointing towards you. So out of the page, baby. All right, nope. We could have used our right hand rule. And I know some of you are like, I just use a right hand rule to power. That's fine. Use your right hand rule. Velocity going that way. Again, keep those nice right angles. Velocity, the force, rotate your hand till your force is downward, and you'll see that that gives you a magnetic field into the page. But because I use my right hand, I need the opposite, which is ta-da, out of the page, baby. All right. Hopefully you're doing all right. If you have questions, just send them over to me. Send me an email. I'll help you out. Okay, next question. Is the charge positive or negative? So we see this charge. It's coming into the magnetic field, and we see its path going like this. So why is it going in that circular motion? We learned that circular motion requires a force. It doesn't just go in a circle. It needs a force. It needs a centripetal force. And the centripetal force has to be in what direction? To the middle of the circle, right? So we know that there must be a force towards the middle of the circle. All right. Now let's use our right hand rule because we don't know. So we may as well use our right hand rule. It's going in this direction. Okay. We're looking for a force. This is an external field. This is an outside field. Okay, so I'm using this right hand rule. Let's look just at the top. Right here at the top, the velocity was in that direction. Okay, so that direction, I need to turn my hand so that the force is downward. What direction do you see the field there? This says the field needs to be out of the page. So in order to get that force, if this were a right hand rule, positive charge, I would need a field out of the page, but I don't have out of the page. I have into the page, which means that this must be the opposite. It must be a negative. Another way to think about it is if this were a positive charge going this way into the field, the force should be upwards. Because the force is opposite, it must be a negative charge. We can even check it now that we know it's a negative, going that way, field into the page, thumb down. And note that you can check this at any point along that curve. Right? At this point right here, the velocity is kind of downwards there, right? So again, we could check it with this. We could say downwards into the page. Look at that. Look at what direction my thumb's pointing there. It's pointing to the left. I know my right and left. There we go. Right that direction. Perfect. Perfect. Very good. So we just found out that it must be a negative charge. Pretty snazzy. Pretty snazzy. All right, last question here. What will happen to these two wires? All right, so now you're like, what are the wires? Well, you got to be able to picture this, right? What does the X mean? The X means is that there's current going into the page. So this is a wire like this, right? Sticking out of the page. The current's going this way into the page. This one right here, current's going out of the page. So the wires go in this direction. We're just kind of seeing a cutout section of it. Okay. Now we had something almost exactly like this in your homework. Okay. The first thing that we're going to do is we're going to look at the field that this one is creating. Okay. So the field created by this, that's the second right-hand rule, first one, current's going into the page. Field would be down over there. It would be to the left. It would be right, thumb into the page. I'm going into the page because it's an X there. Over to the right, right? You can get an idea of the direction of the field going around this way. Okay. Now, because it's going this way and this current is going through that field, what's going to be the result? What's going to happen to that wire over there? Well, now we're looking at this charge moving through this field, which is an external field. It's coming from somewhere else. So we're going to need our other right-hand rule, the one with all the nice, beautiful right angles. Okay. So we say the velocity here is out of the page. The magnetic field is down. Okay. So I'm going to have to be creative with how I hold my hand here. I'm not holding my hand. I'm just putting my hand in that position. So velocity coming out of the page, magnetic field here is down. And what do you see happening to my thumb there? The thumb is pointing over to the right. Okay. So I would say this one is feeling a force to the right. Okay. Now I'm going to do exactly the same thing, but we're going to do it for the other wire. So we're going to get rid of these guys. We're going to say, okay, what kind of field is this guy creating? Okay. Because I'm finding the field being created, I'm going to use this right-hand rule. Okay. Current out of the page. Over here, it looks like it's going up. Over here, looks like it's going to the left. I'm going to switch sides. Over here, look at that. Coming out of the page. Magnetic field is down. And then out of here, going over to the right. So we can see the magnetic field's going around this way. Just like that. Now, just like that. Now, we're going to decide what the force is on this wire because it is in the magnetic field created by this guy over here. All right. So we've got the current going into the page. We're trying to find the force. We're using this guy, right? Current is going into the page. Magnetic field is downward. So into the page downward. And what direction do you see the thumb? Thumb is pointing to the left. So what we're seeing here is that if the current is going opposite directions, this one's coming out of the page, that one's going into the page, with two parallel wires, they're going to be repulsed. They're going to push away from each other. All right, that's some problem solving for you. And we went through each of those steps. We did a couple of different things. Hopefully that was helpful. Please feel free to go back and watch it again. Please feel free to email me if you have a question. Hopefully that this is helpful in going through a whole bunch of different examples. All right, that's it for today. I'll see you next time.